Let's continue with statistical methods, aka data analysis, aka Fourier analysis, for these initial weeks. Is there anything from last session that you would like to clarify before I go on? Yeah, just make sure that you study the material and that you also look into the study questions that are in PMFN, because these will be the questions that are, there are two reasons to look into these questions. One reason is the pragmatic reason that these are the questions that will be there in the exam. The other, maybe less pragmatic reason is that they really emphasize the important aspects. So there are always things that are more important. There are, from the general perspective of the whole narrative, and the study questions emphasize the crucial things that are important for the whole narrative. So, make sure that you work on them. Yeah.
I've got a question on
the
study questions. Because, for example, in the calculus script, I took the study questions, and it was only the first two that we had discussed here in class. But I don't know if we will get to the others, or if we're going to work those others. Yeah,
partially. So we definitely, for the calculus, there's quite a lot in the calculus section, like all the stuff on multivariate and optimization and so on, that we don't need right now. So in the very end of the term, or at the end of the term, you will get the pool of questions that then leaves out some, so you will know what's going on. And for the moment, focus on what we discuss in class, right? So if we haven't discussed Taylor series in class or so that's nothing you need to worry about much. But the only thing, so today we talk a little bit more about calculus in terms of integrals, but mainly definite integrals. So with this, so with sets and functions and calculus, focus on what we do in class. Sorry, my nose is saying paper. I'm dying here. Thank you. So thanks. Right, you don't have a cold? I think it's just because it's so cold in this room. So focus, thanks. Focus on what we discuss in class, and focus mainly on Fourier analysis and less on the calculus stuff. But you will see what we need and what we're not. And in the end, you will get exactly the questions that you will get in the exam, so that everybody will pass this course. Yeah? Any other questions? No. Good. Then let's continue with the discussion of the real Fourier series representation of a univariate real function. So first thing to discuss today is maybe the task that we're actually facing right now. Then, before we can develop a way to address this task, we need to remind ourselves of basic definite integrals. So something that you really learned in school, nothing fancy. Then we can actually talk about the real Fourier series representation. Let's abbreviate this, real Fourier series representation. And then once we talked about that, it's kind of the derivation or the proof for the real Fourier series representation. And I think this will be where we will get up to today, and possibly we talk a little bit about periodic and protracted functions, but I think the complex form then will be left for next week, I assume. Okay, so again, the tasks that we went up to from what we discussed last week. So remember that we want to make this switch just now briefly between the time or space domain of a function to the frequency domain or Fourier domain, and that the fundamental idea is that we have a function here, so some univariate real-valued function, and that we somehow get a frequency representation of that. So in terms of the amplitudes of certain frequencies in this function, where we then have frequency on the x-axis, and here we have, for example, time or space. So that's the overall thing that we discussed at some length last week, and that we can also, of course, invert this. So if we have a frequency domain representation, that we can go back to the time or space domain, which is actually called in MR. This is in magnetic resonance imaging. This is called image reconstruction. And so far, we discussed the case that we actually deal with analytical objects in the sense that the input data, so this is what we have in the time or space domain, are univariate real-valued functions. The difference to the real-life situation is that these are analytical entities in the sense that, first of all, they're defined on the whole set of real numbers, and then there are these little formulas usually that allow you to evaluate these functions. In real life, so in the data analysis context, you only have some data points which you can plot as individual data points over space and or time, and we actually want to get to this, but and how this can be transferred to the frequency domain and vice versa. But to get there, it makes sense to go this way via the analytical mathematical route. And then we discussed last time at length the basic building blocks, and went up to the question or the task, essentially, if you are given a function f, and more specifically, of course, all the values of the function fx, is it possible to find circular frequencies omega k and amplitude coefficients ak for generalized cosine functions and bk for generalized sine functions, so that you can express each value that the function takes on as an infinite sum of what we call last time and discussed at length generalized cosine and sine function, which are still of this form. So this is what we called first we call it a linear combination of generalized sine and cosine function, and then with going to infinity here, we discussed that this also is called a series, which we've also seen in the definitions of the exponential cosine and sine function. And the task, so the game right now, if you want, is you, or I don't know how we want to play it, either you give me a function f. So for example, you say f should be the following function. Let's say something familiar. X should be this, f should be this function. And then the task for me is to find the omega k, ak, and bk so that this equality here holds. Yeah, can also play the other way around. I decide on a function, and you have to find the ak, bk, omega k. And so that's the fundamental task. From a mathematical viewpoint, there are actually two questions. One question is this actually possible at all? If so, under which conditions is this possible at all? So how must a function f be so that this representation actually is defined and maybe even unique? So these are mathematical questions which are interesting, but we will mostly neglect. There's a second question that comes with that is, if under certain conditions this is actually possible to do that, and one knows that, how can we actually evaluate the omega k, ak, and bk, so that if we know that this is possible, how can we get from the function f to these frequencies, so the omega k, and to the coefficients. Yeah? So, and this is what we will look at. The reason why I'm focusing not so much on the mathematical question of whether this is possible at all and under which conditions is that in the end we are only doing this really to establish some knowledge and concepts for a data analytical context. So in a data analytical context where things are discrete, you can always do it. Because the things that you need to do, like integration, will become summation and so on. So this question of whether this is possible at all and under which conditions is in a data analytical context not that important, because there it's always possible. In a mathematical context is of course very important, but we are of course doing statistics, data analysis, so we are more interested in why certain things look a certain way. So I'm focusing more on actually the how rather than the if with this evaluation. And yeah, so that's the task. Yeah, question about the task right now?
So wouldn't it be possible if it was continuous? If data were continuous? Or?
Yeah, data is never continuous. So in the digital age, data is, I think it never was, but still it was treated somehow. So when people had the oscilloscope in the old days, and then they had this pen that wrote their signals onto paper, they treated everything as continuous. But at one point, Bill Gates came around, and then all data was discrete. So whenever you represent something in a computer, like a function, then with numerical values, then what you allocate to each x in terms of an fx is a discrete representation. It stops at one point because a computer only has finite memory. Yeah, so real data is never continuous. So, of course, there might be some, if you do some symbolic computation and so on, then you kind of have models of continuous things. But the standard data that you acquire as a neuroscientist is of discrete nature.
So that I understand that the linear combination is the frequency domain, which every function has to be translated to.
Yeah.
By finding the parameters.
Exactly. Yeah.
Okay. So we're like doing setting these equations equal, and then
we will do something. Yeah. Exactly. Yeah. So definitely. So this is. So if we have this representation, so here it's not quite that, because what we are doing, we are not quite there yet. We are not quite here yet. So this is what I'm doing right now is a real Fourier series, which is a representation of these values of a function in terms of this series. So here you see the x, and here you see the x. What this really refers to here, this transfer from time domain to space, from time and space domain to frequency domain, this is actually Fourier transform. And inverse Fourier transform, and we are not there yet. So, but we need to establish first the ideas of a real Fourier series representation, and then also the complex form of the Fourier series representation, so that you can understand the formula that underlies the Fourier transform. Yeah, because in the Fourier, the basic reason is that in the Fourier transform formula involves a complex exponential. And then if I would show you the formula for the complex exponential, for the Fourier transform, and say here, complex exponential, the link to frequencies and sine and cosine function is completely lost. So we have to go this way. Yeah? So we will, so the longer outline is that we will first talk about the real Fourier series, and then we talk about the complex Fourier series, and then we talk about the polar Fourier series, and then we have all the knowledge that we need to understand the Fourier transform, which is this thing in the end. Yeah? Good. Other questions? Good. So that's the task. So to actually compute these omega k, ak, and bk under certain conditions, and this will involve integrals. So we have to briefly remind us about integrals and what these integrals really are Riemann integrals, and we are also at this point mainly interested in definite Riemann integrals. So from school, you know the Riemann integral. Maybe it wasn't called that, but this is what you learned. In general math, Lebesgue integrals are actually preferred, which in special cases come out as Riemann integrals. So there are more integrals than the integrals that you learned in school. But we can actually get a long way with Riemann integrals here. So let's go to integrals then. That's the basic integrals section in the calculus part. And yeah, let's just jump right in. So we are talking about, at this point, definite Riemann integrals for univariate real-valued functions. So we are still, and throughout the whole Fourier business, except maybe if we go to 2D Fourier at one point, we are dealing with univariate real-valued functions. And now the definite Riemann integral of such a function on an interval, so a subset of the real numbers a, b, so that's a closed interval where a and b are both part of the set, is defined as the real number, and that's this I now, so that's a number, b, a, f, x, dx, which doesn't say much actually. It's more kind of a way to write things, but you have seen something like this. So who has seen this kind of integral notation in school? Everyone has seen that in school. Very good. So what is important about this? So the first thing with these definite integrals is that they are real numbers. Yeah. So that if you see this kind of expression where you have this integral and then you have a lower boundary a and an upper boundary b, and then you see this fx dx, what you should see behind this is that if now there is an actually defined thing that is the function, so that you actually know what the function is and that there are actually numbers a and b, then this is a real number, right? It's something like 4.2 or minus 3.1 or something. Yeah, it's not some fancy snake-like symbol-y thing or something. It's a number. Yeah. If a, b, and f are defined. So that's important. Why do we call it a definite integral? Because there's also an indefinite integral, which we will briefly introduce as well. And then you should mainly see this whole thing as notation, and specifically don't think much about this dx here, what that might be. This is nothing. This is just notation that comes with this integral sign. You often see there are variations on how people write integrals, which is sometimes a little bit annoying. So some people think in physics specifically, they write the dx first and then the fx. It's complete madness, but you see it. So it means the same thing. Good. So what is the intuition behind the integral? Does anyone actually know that? Not from the math people, somebody else from school. What do you remember from school about the integral?
I think it's like all the space in between the function and the x-axis.
Exactly. And all the space with respect to a and b?
From a to b.
From a to b, exactly. Yeah, so that's exactly the intuition. So it's the area under the curve, it's sometimes called, although what you said is actually more specific, because the area under the curve doesn't say that it's up to the x-axis. So area under the curve is maybe not the best thing to say. Yeah, and the common way to maybe first state this in terms of equations is that one can imagine basically discretizing the interval from a to b into little intervals that have a width of delta x. So looks then like this. So if you have x n or I minus 1, let's make n minus 1. No, let's make I minus 1. I minus 1 here and xi here. Then if you do xi minus 1, you get this delta x. So that's just the length of this thing here. So one can discretize the interval in, of course, with a finite number of steps. So here I somehow end up on n plus 1. You can also end up at 1, depends on how you do the whole thing. But I think for the formula that I'm using, it needs to go up to b n plus 1. B being n plus 1, and then the idea is that one can approximate, and this is also if you use a computer to evaluate integrals, approximate an integral by a finite sum, where you again have the sum symbol, of course, and you go from x1, so you evaluate the function f at x1, and then you go up to n and you multiply each of these values with the width of the interval here, and then you can do these things if you are into limiting processes where you let the width of these intervals go to 0. There's actually a little proof of how this is to be understood in terms of this limiting process. I thought there's one. Yeah. But we will not go over that. So rather than going over that, I actually show you the figure to that, which I think explains a lot. So let's go here. Definite integrals. Should get clearer. Hello. Why is it messy? Looks a little bit messy, right? Because my Adobe doesn't want to play with me anymore. Then let's go to PowerPoint. So this is now this formula visualized. So the idea is that you have a function f, and here you have plotted the graph of the function fx. And then basically what you said is that one tries to approximate the area between the function graph, or this fx here, and the x-axis. And what this little formula means is that you have fxi, so this, you look at xi and you evaluate fxi, so then you are at this corner here. You see this? Yeah. You are at this corner here, and this corner, and this corner, and then you multiply it with the width of the interval, which is here, it's this delta x, it's this thing. So this is here shown exemplarily for fx2 times delta x, which is this rectangle. So you all know that the area of a rectangle is the width of the rectangle times the height of the rectangle. So that's this gray area. And then to approximate this integral, you so from a, so a would be x1 and b would be xn plus 1. There's a so here it needs to be xn plus 1, and then there needs to be xn, which also fits nicer actually on the graph. Then you sum all of them up. Yeah, so that's essentially it. Of course, there are different ways. If you do numerical integration, there are different ways to do it. So you could also say that instead of using the left endpoint of each of these subintervals here, you rather would take the average of the function over the little interval, and so on. So these are all different ways to do numerical integration. But in terms of the intuition, and this is what we are trying to focus here right now, it's that you make these little rectangles and then sum them all up. Yeah? Questions about this intuition? No? End of slideshow. Good. So that is what this is supposed to mean. And then, of course, you need to that one other thing that is important about this, if you have an integral that actually, or not if you have an integral, but if you have a function that is like this. So if you have 0 for y here and 0 for x, and this is -1, and here you also have -1, and you evaluate the integral of this thing here, this is of course negative. So an integral is the signed area under the curve, it's not the absolute area under the curve. I mean, this is relatively straightforward if you think about that. If you evaluate this function here, f, then these values are all negative, and if you just multiply them with these rectangles, then, with the width of these, then you get something negative. So that's something to keep in mind, and also something that we will need in a second. And then one can actually use this sum representation of definite integrals to establish something quite important, namely the linearity of integrals. And I think I rather state it rather than write it all up. So the thing is, if you have two functions, if you have the sum of two functions of which you compute one integral, then you can decompose this into the integral of fx plus the integral of gx. This can be, based on the sum formula, this can be made very intuitive if you are happy with the linearity of sums, essentially. So if you went over the sum symbol stuff in the script or in the videos, then this thing follows directly from how sums work. The same thing, and this might even be more helpful in actually evaluating integrals, is that if you have a constant in there that does not depend on the integral variable, so if you multiply a function by a constant c, then you can take the constant out of the integral, which again follows directly if you are happy with this sum approximation of the integral. And this is, in actual computations, that's quite helpful. Yeah, I don't think we will. Do we need this? I don't think we need this a lot right now, but in general, it's really helpful. Good. And then, of course, the question arises now how to compute actual integrals. And does anyone remember from school how you compute integrals? So if you have a function, let's say 2x plus 1, and you're supposed to compute the integral from on the interval 0 to 3, what would you do? So how would you go about it? Not so. Just tell me the strategy. Not. I know that you need to evaluate some things, which I don't tell you right now because otherwise I'll tell you the answer to the question. But just the strategy. So what's the first thing that you do if you want to compute this integral? And how do you do it?
Please take a shortcut wrong. Just keep replacing x with 0, 1, 2, 3.
Sorry, replacing x with?
0, 1, 2, 3.
0, 1, 2, 3. I'm not quite sure what you mean. So you are about to. Okay, so you're trying to do a numerical integration. Yeah, that's fine. So you propose to, I guess, do the numerical integration via the sum formula that I just showed you, which of course is a good idea. But actually, I was talking about now doing the analytical evaluation of the integral, which you don't do by sum formulas, but in school you did that. How?
I'm not so sure about the English word for it, but you don't have to do it.
Stammfunktion.
Yeah, exactly. So not the direct derivation, but the other way around. So the original function of this one.
So sorry, can you say it again?
The original function.
The original, so it's called, the Stammfunktion is antiderivative.
Okay.
Yeah, the entire.
Okay.
Yeah. So, and what do you do with that?
Then you have to compute the function word, some function, the function value for 1 and 0, 3, or 0 and 3, and differentiate.
Differentiate? So what do you mean by
So
differentiate?
you have to basically function the value of the capital F
Yeah, so that's the antiderivative.
of 3 minus the capital F of 0.
Yeah. So that's what you want to do. Yeah. So exactly. So that's the analytical way to compute integrals. So you form the antiderivative, and then you use this fundamental theorem of calculus, which states what basically you just said. For some reason I have S here, but works with dx as well. So you form the antiderivative and do fb minus fa, and this is what you practice in school quite a lot. Of course, this requires the notion of the antiderivative, and it doesn't hurt at this point to briefly remind us about the idea of the antiderivative, because in some way we will need this also for differential equations later. So the antiderivative, or in German Stammfunktion, can be introduced in terms of the indefinite integral. So that's the last thing in terms of integrals that I want to mention. Because this is sometimes forgotten, especially so sometimes people, once they know about definite integrals, they think that all kind of integrals are these definite integrals which are numbers, but that's not the case. It's a little bit like with the derivative of a function in a point versus derivative as a function. Yeah? So if you evaluate the derivative for each value in the domain of the function, then you get a function itself, and this is also called the derivative. And the same, in a way, applies for integrals in the sense that you can evaluate the definite integral over an interval, and you can evaluate the indefinite integral, which is itself a function. Namely, if you have a univariate real-valued function, then the indefinite integral f can be defined as a function from the positive real numbers to the real numbers, which is defined as, now I know where the s comes from, as the integral from 0 to x of the function fs ds. Yeah. So the important thing is that the function argument here is the upper border of this definite integral. Yeah. So the definition of this indefinite integral works that we know what a definite integral is, so we can evaluate this. Now we evaluate this where we keep the lower boundary of the integral fixed, and now we evaluate all these definite integrals by changing the upper boundary. And then something rather surprising happens, namely that one can show that the derivative of this indefinite integral, which you either write this way or you write as dx, this is at this location, so at the location x is the function itself again. So this is fairly intuitive. So it's you all know that the antiderivative, just by its name, if you compute the derivative of the antiderivative, you get the original function again. However, if you look at it this way, so that you have here these definite integrals from 0 to x, and then you somehow compute the derivative of this integral here, that then the function fx pops out again. Somewhat surprising. I put, for this, I thought I also had something for the other thing. Confused now. I put a proof of this in there, which makes this intuitive. So essentially it shows that you can go both ways by means of the definite integral. So you can go from a function to its indefinite integral, which means it's antiderivative, and then by computing the derivative of the antiderivative, you can go back to the function, which is also quite important if you're thinking about later of differential equations where you have the derivative of a function and you want to go back to the function itself. It means you need to compute the antiderivative. I put a little proof for that, inspired by the Leithold stuff in the script. So have a look at it if you are into figuring out why this actually holds. Just a little bit of a warning, it needs a mean value theorem, I think. So you would have to look up what the mean value theorem for integration actually is. Good. I think this is about as much as I want to say about integrals. So from a practical perspective, even if this is not really clear to you, I think at this point, because you haven't gone over the proof, I hope it's not really clear to you. If it would be clear to you, either you know it, then it's fine. But if you think it's completely clear, but you don't know how this the proof works, then something is a little bit off. So anyway, so what you are familiar with is how to compute antiderivatives of certain things, right? So if you have a function which is a constant, then you know that the antiderivative of this is can be written as this, and this you then always know how to check, because you can compute the derivative. So if you compute f prime x then you know that a constant, if you compute the derivative with respect to x, constants go away. And here you do this thing that you always do to polynomial functions. So you take, here you have x to the power of 1, so you subtract 1 from the exponent, so you have 0, so you get 1, and 1 goes in front of it, so you end up with a, which confirms that this is the case. And then what you really practice in school a lot is to compute the antiderivatives and derivatives of polynomials. So you know that that's correct, I guess. I hope that if you go the other way around, so if you have x to the power of b and you compute the derivative of this, so maybe like this, then you get b x b minus 1, and this is why there must be a plus 1. So this thing you did a lot, right? So you all know this 4x squared, compute the derivative, it's 8x. So this kind of thing I'm just reminding you of here. Yeah. And yeah, maybe the although we actually don't need it, but so in terms of the functions that we are currently interested in, if you have the sine, last week we went about that the derivative of the sine is the cosine, and the derivative of cosine is minus sine, so the antiderivative of sine is then minus cosine plus x, plus c, sorry, minus cosine plus c. So if you compute the derivative of this function, the c goes away, and the derivative of cosine is minus sine, so the derivative of minus cosine is sine, and then you're back there. And for the cosine, it's even simpler. The antiderivative is just sine x. Yeah. So these are kind of the little things about Riemann integrals that you should be happy and familiar with. There's an example in the script that you can look into, and that also combines these two notions of indefinite and definite integrals. There are some study questions related to that. So look into this basic integration from school. That's what I'm trying to say. Yeah. So that you are happy with integrals. Good. What time is it? Oh, it's almost 1 hour over. But that's fine. So then the thing actually to discuss next is the real Fourier series representation, where we will need integrals. So integral signs will come up, and I reminded you of those now, so we can have a little bit of a refreshing break, and then we go into the real Fourier series representation of a univariate real-valued function.